Okay, we are returning to diagonalizing, so let's just go practice one. So if I say diagonalize a 2 by 2, I won't give you the eigenvalues because I'll want you to go do that. So how you do that, remember, is the determinant of a minus the lambda I. So let me try to make this neat enough so you can read it. Okay, so I'm going to find the determinant of this, which is 1 minus lambda, 2 minus lambda, subtract a 12, and set it equal to 0. So I have to multiply this out. And it's equal to 0. That's the characteristic polynomial, remember. So I get minus 3 lambda. Oops, I meant 12 there. Okay, I'm thinking of, what did I do? This is a 2. This is a 2. Okay, let me make sure I multiply this out right. Yes, okay. So minus the 3 lambda and then a minus a 10 equals 0. So let's factor this out. Okay, so I get 2 eigenvalues, a 5 and a negative 2. So remember, so what to do with lambda equal 5? So I have to take a, subtract 5i. Well, let me put the 5 inside. 5, 0, 0, 5. So let's figure out what this matrix is. So 1 subtract 5 is negative 4. 3 subtract 0 is a 3. And that's a 4. 2 subtract the 5 is a negative 3. Okay, so this is my matrix, right, for 3, I was saying it wrong, negative 4, 3, 4, negative 3, and I'm solving this to find the non-trivial solutions, right? So if I put this in my calculator, I guess it wouldn't be that hard to do it by hand as well. I get to this for the augmented matrix. So that means x1 is 3/4 x2, so my vector x1 is 3/4, and x2 is itself. Okay, so and I'm going to change that to multiply both by 4. So this is the vector that goes with the eigenvalue of 5. So let's just start putting together my p and my d. So here's my 5, 0, and here's my 3, 4. So now I'm going to do the same thing for negative 2. So I'm going to have my a, and I'm going to be subtracting off a negative 2, so it's going to be a positive 2. So this gives me the matrix 3, 3, 4, 4. All right, so I'm going to augment that with zeros, row reduce it. So that's not too hard to see that I get 1, 1, 0, 0, 0, 0. Okay, so this means x1 is equal to negative x2. So my vector x is negative 1, 1, right? Factoring out an x2. Okay, so what that means for my p is I have a negative 1, 1, and for my d, I'm putting in the eigenvalue of negative 2. So there it is diagonalized. That's all you have to do. All right, so let's go through this one a little harder, right? Got 2 eigenvalues. I'll always give you the eigenvalues if it's a 3 by 3. So let's go through for eigenvalue of 2. So I'm going to go slow so I don't make a mistake adding or subtracting. So I'm going to be subtracting this off. So I get 1, 1, 1, 1, 1, 1, 1, 1, 1. Oh my goodness, there it is. Okay. So I'm augmenting this with 0, right? So I'm taking this, x equals 0, and so row reducing, I get okay, so what this means is x1 plus x2 plus x3 is 0, right? So x1 is negative x2 minus x3. So remember, I'm trying to find the vector x. So I would get negative x2 minus x3, x2, x3. So if I factor an x2 out, I get a negative 1, 1, 0. And if I factor an x3 out, I get negative 1, 0, 1. Okay, so putting together my p and my d. So let's put p here. And I'm going to put these 2 vectors in first, and my d, since this is the eigenvalue of 0, I'm going to put the, eigenvalue of 2, I'm going to put the eigenvalue in there, those 2 places. All right, so now I'm doing the lambda is 5. It's 1, 1, 3, and I'm subtracting off a 5, 0, 0, 0, 5, 0, 0, 0, 5. Okay, so this gives me a -2, 1, 1, a 1, -2, 1, and a 1, 1, and a -2. Okay, so again, I'm solving this. I'm just going to write it down just to make sure you remember this is what we're doing. We're trying to find the non-trivial solutions, right, to this. So if I put it, row reduce it, put it in my calculator, I get 0, 1, -1, 0, 0, 0, 0. Okay, so what this means is x1 minus x3 is 0, x2 minus x3 is 0. So my x1 is positive x3, and my x2 is positive x3. So my vector x, which is x1, x2, x3, it's x3, x3, and x3. So I get a 1, a 1, a 1. So that vector 1, 1, 1 corresponds to that. Okay, so now we're ready to move on to section 7. Because now what we're going to be doing is we're going to be taking symmetric matrices. So what is a symmetric matrix? So that means it doesn't matter what's on the diagonal, but these two will be equal. These two will be equal. These two will be equal. So I could fold the matrix across this diagonal, and I'd see that there's a mirror image. All right, so they're telling me to orthogonally diagonalize this matrix, and they're telling me the eigenvalues. So the eigenvalues are 7 and -2. So I'm going to skip the work on this one because I just did it a couple of times, right? So we just did something similar to this. So eigenvalue of -2 would give me this vector, and eigenvalue of 7 gave me these two vectors. Okay, so what does it mean to orthogonally diagonalize? So these two vectors are linearly independent, but they're not orthogonal. And so how do I make an orthogonal diagonalization? So I need to make these orthogonal to each other, and that's where the Gram-Schmidt comes in. So the Gram-Schmidt will make them orthogonal. So these are the two vectors that I need to do the Gram-Schmidt on. So I'm going to, remember, you always pick one first off. So if I call this, I'm going to make this one equal to V1. Then I say, okay, now for V2, what I'm going to do, and I change this on your handout. So this should be an X2, right? And this is an X2. So this is an X2 and this is an X2. And that's correct on your handout. I just forgot to update it before making this recording. Okay, so this is what I'm calling X2, right? So this is my X1 and this is my X2. So X1 I made equal to V1. So this is my X2. So let me show you what I did. So X2 is -1/2, 1, 0, minus, so I'm dotting X2 with V1. So -1/2, 1, 0, V1, 1, 0, 1, and then 1, 0, 1, 1, 0, 1, and that all gets multiplied times V1, which is 1, 0, 1. Okay. So -1/2, 0, I'm sorry, -1/2, 1, 0, right? This is this, carrying it along. So now let's go do this. So here I get a -1/2 and a 0 and a 0. So a -1/2 with this negative in the front turns into a 1/2. Then doing the dot, or the dot product here, 1 and 0 and 1, so that gives me a 2. So then 1, 0, 1. So what do I get here? I get a 1. Uh-oh, what happened? I'm supposed to get a positive. This is supposed to be negative. Hold on, what did I do wrong? -1/2, 1, 0, -1/2, negative, but then there's the negative out here. Nope, I guess I'm right. Okay, so this is, let me just write it again. So this is -1/2, 1, 0, plus a 1/4, 1, 0, 1. Okay, so I'm going super slow here because I'm making mistakes I shouldn't be making. 1/4, 0, 1/4. Okay, so adding a negative 1/2 and a positive 1/4 gives me a negative 1/4. 1 plus a 0 gives me a 1. A 0 plus a 1/4 gives me this. So this is my V2, my orthogonal vector. And you can adjust these vectors, right? So I'm going to multiply that by 4 to get to here. So these are the two that I just made orthogonal, and this one is automatically orthogonal. So these three, and I'm just going to make this one nicer by multiplying it by 2. These three are my orthogonal basis, and what I want to do is I want to make it orthonormal. So how do we make it orthonormal? So I take this is my first, right? This is my first column. I'm going to normalize that vector. So how do I normalize a vector? I find the length of it and I multiply by 1 over that. So the length of this vector would be root 2. So I multiply 1 over root 2. So that's what this is. Then I'm going to, so these other two are these two normalized. So it's an orthogonal and a normal, so it's called an orthonormal basis. All right, so here is one for you to do. And I'm going to just write down the answers for you. If I had them. Oh, no, I do have them. So the answer is right here. There it is. So you get to find the orthonormal basis by finding the vectors and normalizing them at the end.